start off with some questions from the other night on the homework. So just put in the chat if you have any questions from the other night, or raise your hand and we'll take you off mute. I also want to see if everyone can like type in the chat and see how far along you are. If you guys can write if you were caught up or not. So if you can type in if you're caught up or how behind you are as well. Kind of want to gauge that again.
So John, we'll cover that today at the start of the lesson, the stalls with G-forces. So hopefully after today, maybe you'll feel a little bit better about that quiz.
Yeah, I just had to go back and write them down a little bit and just kind of memorize. I mean, because they'll ask for one or they'll give you two, and then you got to figure out number three, or so they'll kind of change up the process. They'll give you two of the the known factors, and you just got to try to figure out the third factor by
right
whether or not it's the square root or not.
Right.
So it looks like we got a good majority of people caught up. Sorry that you're sick, Eva. Hope you feel better. And don't worry about it. Take your time with getting better. And Yvonne, that's okay. I mean, you're all over the world all the time, so understandable. Okay. But yeah, I'm glad to see that a lot of you guys are caught up. That's really good.
Jay, do you want to do us to like explain anything on the compass before we get started? Or do you want to save that for Friday or?
I don't want to take up other people's valuable time on this. I'm going to do it again in the morning when I'm fresh.
Okay.
If I have questions, I might call tomorrow and just see. I don't know. I just have a brain impasse. I don't know.
Okay.
But
we can do that Friday
Yeah.
as well, because that's what Fridays are for. So don't feel bad
Okay.
about taking other people's time. I'm sure someone else has questions on compasses
Okay.
as well.
Okay. Thanks. I appreciate the offer, Nick.
Yeah.
But I don't want to take other people's time. But let me try a few more times, and I will write down what I think is my block, and we'll go from there. Thank you, sir.
Perfect. Sounds good.
Sounds good. All right. Well, if there's no questions, I'm going to get started with tonight. All right. So tonight we're going to finish up our conversation about stalls and the load factor and how to recover from them. We're also going to talk spins and then finish up the rest of the forces. So weight, thrust, and drag. And then we're also going to talk about wake turbulence and ground effect as well. All right, so to recap from stalls, so remember this chart here, it showed our lift increased with our angle of attack pretty linearly all the way up until we met our critical angle of attack, which is shown in these dashed red lines here. And at this point, when we exceed the critical angle of attack is when we stall our aircraft. And students get confused a lot what causes a stall because they hear of a stall speed and figure if you go slower than the stall speed, you will stall. While this is true, the speed at which an aircraft stalls changes with the configuration, the bank angle, load factor, and more. Therefore, it doesn't exactly explain what happens in a stall. But a stall occurs when we exceed our critical angle of attack, and to recover from a stall, we have to get an angle of attack that is less than the critical angle of attack, and the critical angle of attack can be exceeded at any airspeed or at any altitude. And just to kind of recap with how we stall again. So we previously talked about the airflow staying attached to the aircraft wing and conforming to the wing shape. And this happens because of the surface friction between the air molecules and the surface of the wing in something called the boundary layer. So that's between the surface of the wing and the relative airflow. And then as our angle of attack increases, the air on top of the wing has to turn an even sharper corner. When it does this, the momentum of the air eventually becomes too much such that it overcomes the force of friction, and the friction just isn't enough to keep it attached to the surface of the wing, and it detaches. And then what happens here is eventually we get to our critical angle of attack, where the air on the top of the wing can no longer stay attached, and it completely separates away from the boundary layer and grab of friction and turns into what we call turbulent flow. And that, instead of smoothly flowing over the wings, it flows in eddies and turbulent vortices, as depicted here with our red arrow. And the lift is completely destroyed, where we were getting from Bernoulli's principle and the pressure differential above and below the wing and Newton's third law. And this aircraft is considered stalled. So as you can see here with this airfoil here, we just stalled, and we have our eddies and turbulent flow, and the lift was completely destroyed. And here's that visual depiction again, like we talked about from the other night. So we have our airfoil here. We start pitching up and up until we eventually exceed our critical angle, and then we have the eddies and the turbulent flow there depicted graphically. So is there any questions so far on the recap from the other night?
I think that top picture in the green there just, I mean, it kind of spells it out, because you see the blue when it's, in, the slipstream, so to speak, and then it just, meets that critical angle and it just throws it off. It's pretty wild.
Yeah, no, it really is. And if you've ever been up with your instructor doing stalls, it's a pretty fun maneuver to perform. Did you have a question, Jay?
Yes, quick question, and I think you mentioned it, but you can stall the wing out depending upon speed, weight of the aircraft, but when you reach that angle where it stalls and loses lift, it could happen whatever you're doing to the bird. In other words, what I'm trying to say here, it's if you reach that, whether you're climbing or you're coming in or you're making your turn in for your final, as long as you stay in a stabled attitude and you keep the airflow on the wing, you're good to go. But if you violate that, this can happen, and that's bad news.
Yeah, so so if you exceed your critical angle of attack at any point, it doesn't matter, you'll stall the aircraft.
Okay. All right, thank you. I'll leave it at that. Thank you.
Okay. All right, so now we're going to talk about what John was kind of hinting at earlier with the load factor in our stalls. And the additional weight carried by the wings divided by the weight of the aircraft is defined as our load factor. And here's a nice equation that we have. Don't worry about the equation, though, or memorizing it. This is just something that Nick added to kind of give like a little bit of the why behind, load factor. And it relates to load factor, and N is the lift and the weight force is on the bottom. And then the load factor, there's the lift over weight. Is it lift over weight? Or was it load over weight?
It's lift. So N is the load. Yeah, N is load factor, and then so the ratio of lift to weight is equal to your load factor or your G forces.
Yeah, so this is what you would use to calculate how much G force your aircraft is pulling at the time of your maneuver. So for this example, so if lift and weight were equal to each other, which we would need for straight and level flight, we would have a load factor or a G force of 1. So as you can see, if my lift and my weight were equal, we would have one load factor, or 1 G's we would be pulling. But let's say if we increase the lift compared to the weight, the G-force increases. So think of a fighter jet that increases the angle of attack and speeding up. This would increase the lift significantly compared to the weight, and the pilot would feel those Gs. So I know we'll probably get into this later on in the course, but when we're doing like steep turns, for example, that's another maneuver where you feel the load factor a lot. And when you're doing your steep turns, when you're banking over to 45 degrees, you can feel those G forces as you are doing your steep turns. So in this case, we increased our lift to 10, our weight's still 5, but that doubled our load factor or G's that we're feeling.
Yes, I just want to add, like, if we remember what increased lift, it was airspeed, density, and angle of attack. So that example of like a fighter jet, if you've ever been to an air show and they do like a low flyby and then they just accelerate and climb really fast. So they're accelerating, so they're adding airspeed, that increases lift, and then they're increasing their angle of attack, that also increases lift. So that's why the pilot is really feeling G forces when they do that high G climb, they call it, right? So that's kind of the perfect example of this equation in work there.
Yeah, and I kind of like to think of like the Top Gun movies when they're all flying around and like, pulling really high G's, doing super high speed climbs. I like to think of that as well. And then we can also relate the velocity or the airspeed with the load factor in the N in this equation. And I'll let Nick describe this one a little bit more.
Yeah, so again, don't worry about this. This is just to show. So let's so this is just to show the relationship between airspeed and the load factor, which is N on the top. So Ali, if you can go to the next slide here. So remember this thing, right? AOA or angle of attack goes up. As it goes up, our lift goes up until we reach a critical point. And that's called the critical angle of attack, which we have here, this dashed red line. And then if you go to the next slide, so what is that CL? So CL you can think of is just coefficient of lift. So you can just think of it as lift. So that point at which we reach the critical angle of attack matches up to the point at which we get maximum lift, right? So, and Ali, if you go back to the equation, 2 slides, I think. Thank you. So there's a CL value in this equation. So if we plug in the exact CL value of the CL max, where we have our max angle of attack, now go forward like 3 slides. So if we plug that CL max in, we get this, and the velocity or the airspeed we get at that exact point is going to be our stall speed. So remember, like VS and VS0, when we have stall speed, it's different whether we have flaps down or not. And the reason why it's different when we have flaps down or not is because that S value on the bottom of the equation, that changes. When we lower flaps, it essentially, we increase our wing area. Relative to the wind, relative to the wind, it looks like it's bigger because they kind of extend out and extend the wings. So that's why it's different with and without flaps. But what I want you guys to realize is that our stall speed, now this is an equation for stall speed. It is the speed at which we reach that maximum angle of attack and maximum lift, which that CL max. And it's a factor of N. So if N goes up, right? If N goes up, our V stall is going to go up. So the speed at which we stall is going to go up. And so that means if our G forces go up, our stall speed goes up. And so let's see what I'm trying to think. Yeah, so I think that's it. Ali, I think you can, well, actually go to the next slide. So we want to be aware of things that increase our stall speed, especially when we're flying at slower speeds, like during takeoff or landing. So we might fly an aircraft. So a lot of trainer aircrafts have a stall speed around like 54, 55 knots for like VS1. So that's a straight and level flight, right? That assumes our load factor is 1. And then that same aircraft that have a stall speed of like 54 and 55 knots at straight and level will also have like an approach speed, the speed at which we want to fly as we come down into land, of like 60, 61 knots. So it's not that far off. So if we just increase our load factor a little bit, that will increase our stall speed enough to, let's say we're on an approach, let's say we're 2 knots under are, we're a little bit slow, which is very easy to occur, a little bit slower than our approach speed. So we're at like 59 knots. And then we have to, for some reason, make a turn, or we get a gust of wind, or something changes our G forces and increases our stall speed to above 59. That means we are going to stall when we are above our stall speed. We've reached, according to the relative wind, we have reached our critical angle of attack and our max lift. And a lot of aircraft, they don't have an angle of attack indicator, but they do have an airspeed indicator. So that's why we use stall speed.
Mhm.
And then if you go to the next slide. So we want to know what increases our stall speed. And then the next slide. And I mentioned N already. N is our load factor. That increases our stall speed. And so what increases N? So if you go to the next slide, and then I'll let you take it from here.
Okay. So what increases that is our bank angle. So the steeper we bank, the more load factor on the plane. And I remember like when I was in school, like learning this, we had that it was like that the V speed chart, which is in like I think the PHAC or something, but it talks about the different V speeds and everything, but it also talked about the bank angle. And essentially, like if you bank all the way over to like 60 degrees, depending on your load factor, you're pretty much like um, doubling your load factor there when you're banking over to 60 degrees. So it's really crazy. And your POH also has like your load factor limits. I believe it's in section 3. So your normal operating, it'll talk about your the different load factors, the loads that you can have on your plane. So some planes, it's about like 3 or 4 G's is what your plane can safely hold. It just depends on your aircraft. So you can check that there. Um, Also like accelerating. So obviously when, you see like the fighter jets and stuff, when they're accelerating super fast, obviously that's going to increase lift exponentially. And therefore, like the faster you're accelerating, the higher that you might get to the point where your critical angle of attack and where you're going to stall. And then also climbing, that's going to increase your load factor too, because you're putting more G's on the aircraft when you're climbing. So that's going to also increase the speed at which we stall also. And this was kind of like the chart that I was talking about, that you can see like the bank angle that you have, the more load you have. So the more you increase your bank angle, the more load factor or G's you're going to have on your aircraft. And as you can see, the further you bank, the more load that you're going to put on your aircraft. And this is what's going to get people in trouble because the further you bank, the more load you put on your aircraft, the more likely you're probably going to stall.
Yeah, Ellie, what do you think the average like bank angle range is for like a student pilot? Like,
So when we're doing steep turns, like the furthest we bank obviously to standards is 45 degrees, like with steep turns. But like I probably wouldn't let like a student go past that. Like if you're just doing like, stalls and stuff, like we would usually just keep them wings level with where I did my training at, and then with my check rides, I didn't have to like stall in a bank. I know it's like up to 10 degrees of bank. I think you can have the wings banked in a stall. I think it just depends on the DPE, but you can technically have like do power on and power off stalls like in a bank, but I probably wouldn't let them do like more than like 10 degrees in a bank with stalls just because like you're further putting load on the aircraft, and then you could also potentially like if they don't recover properly, you could get into a secondary stall or potentially a spin. So,
right.
but yeah. Um, then I'll move on to the next chart here. So it's also critical to know the relationship between this relationship because we as pilots sometimes have to bank when we are already flying relatively slow, like when we are in the landing in the pattern, for example. And this is one of the most common causes of pilot-induced stalls and fatalities. Just a 30-degree bank can increase the load factor in the turn and a stall speed by 5 to 10%. And that's pretty significant because that means if you are turning to final and flying around at 60 knots with an aircraft whose documented stalled speed is 55 knots, a bank of more than 30 degrees can increase the stall speed by 5 to 10% or 3 to 6 knots, which is enough to exceed your 60 knot limit and put your aircraft into a very dangerous stall. Because of this load factor effect on stall speed, steep turns are common times to encounter a stall. And steep turns, we'll talk about more of those in a future lesson. But they're one of the private pilot maneuvers that you'll have to do on your check ride. But yeah, as you can see with the chart here, so the further you increase your bank angle, the more the percentage of increase in stall speed goes up, as you can see here. So it's pretty linear with that. And in this example here, we just wanted you to consider a pilot who is turning from base to final, flying near approach speed, but they overshoot the final approach pass and realize it's too late. And so they'll try and overcompensate this by banking even harder to get back onto final by increasing the load factor and increasing the stall speed with each degree of bank until they finally exceed the stall speed by which the aircraft with the aircraft when they already are in a low altitude, giving them not enough altitude to recover. And yeah, exactly what Jay said. You do a go around. If you ever get into a situation like this, and it's probably going to happen to you at least once or twice in your student pilot days when you're trying to, guess where, when should I make my turns, for base to final, or maybe you have a good tailwind pushing you, so you might have turned too late. It's always good practice if you're in this situation. Don't try and overcompensate like the orange aircraft. Do a go around immediately. Like I wouldn't even try to recover from this. Just go around. If you're at an untowered airport, just let them know like, hey, so and so going around. And if you're on a towered airport, just let the tower know and they'll sequence you back in. It's not a big deal if you have to go around. Go arounds are free. No one's going to judge you for those. Just do that because if you get to be like this orange aircraft here, you could potentially stall your aircraft in a very dangerous way because you're already at a low altitude, low airspeed, and it could be a fatal stall. So just do not try and overcorrect and try and get back on center line. Just go missed. Yeah. And another common time we see stalls occurring is after takeoff, and a pilot needs to make a hard bank either to return to the airport in an emergency or for some other reason. Typically, if you're trying to do a turn back to the airport, it's also called the impossible turn. And it's usually when you're trying to maneuver at like less than 1,000 feet AGL and you're trying to do a turn back to the airport. That's why it's called the impossible turn because it's impossible to make this turn without stalling your aircraft because you're already at such a low altitude, you're already at a low airspeed. You might have flaps down too, depending on if you're doing, performance takeoffs like short and soft field, or in my aircraft that I fly, I have flaps 10 put in just because that's what the airplane calls for with takeoff, for normal takeoff. So don't try and do this. If you have to, if you take off and you happen to lose an engine, you can always look for some place to land straight ahead. Don't try and turn sharply or abruptly. I brief this every time I fly because you never know, and you always are looking for a place to land, even if like everything's going fine out in the area where you're at, because you always just want to know, okay, I have an option here in case something happens. So make sure you're briefing that on the ground. Like if we have an engine failure after takeoff, we're not going to do a turn back around. Um, just find a place to land straight ahead. Don't try and turn around because you're potentially going to stall, and that would be pretty detrimental. at such low airspeeds and low altitudes. Let's see. Let's see, the previous slide mentioned acceleration contributing to stalls. Would accelerating increase stall speed if flying and maintaining a steady altitude without turning? I'd assume slower speed would increase the potential of stalling. Um,
So do you want to
you can
take
go.
this one, Alan?
Oh, you can go ahead.
Yeah, so the slower the speed at which you fly gets you closer to the stall speed. Because usually we're pitching up, even when we're straight and level, we're pitching up to be able to fly at that slow speed, and so we're closer to the angle of attack. But to answer your question, yes, increasing. So when we accelerate, like that time during the acceleration, we're increasing our load factor momentarily, which will increase our stall speed, but we're also increasing our speed. So the gap between stall speed and speed remains kind of the same. So, and that's really what we want to pay attention to, the gap between our current speed and the stall speed. So when you're actually like flying, you just want to, again, it's tough to know because you don't have an updated number of stall speed, in the cockpit. You just have to understand that when you do maneuvers that have a change of direction, and a and a change of speed, that contributes, those accelerations contribute to the load factor, and that will increase your stall speed. So when you're slow already, right, and then you increase your load factor, now so when you're slow already, the gap between stall speed is already kind of small. So now when you increase your load factor, you could cross that threshold and stall. So hopefully that answered your question. Ali, I don't know if you wanted to add anything else.
Yeah, I would say another thing too, when you start flying, have your instructor like demonstrate slow flight to you. I'm sure we'll talk about it in another lesson. But essentially that's a good way for you to kind of feel like, maneuvering at slow air speeds, higher angle of attack. Have them demonstrate it to you. I know like this one doesn't technically apply unless you go to like CFI, but there's like, the Airspeed demo, which is basically slow flight without flaps or like different flap configurations, but like have them do slow flight without flaps, have them do slow flight with like one or two or three notches of flaps, because then you can kind of see what it feels like to be cruising around at a slow airspeed and a high angle of attack and maneuvering in it. Because you're putting more load on the aircraft. You're at a slower speed. You're close to your stall speed. So it just kind of gives you that feeling of what it feels like, and it's a very weird feeling. It's very mushy a little bit too, especially like when you're that slow. Um, so yeah, just try and have your instructor demonstrate that stuff to you, and you'll eventually be doing that as well for your primary training. All right, and then we're going to talk about how to recover from a stall next. So with stall recovery, we want to get here. So with this example here, when you stall, your stalls start at the wing roots before they propagate outwards because they designed the aircraft this way to make it easier to recover from a stall because if the wings were to stall at the root, it'd be much harder to recover from them. Wing tips, sorry, not the root. So if we had this, if the wings stalled at the tips, it would be harder to recover from versus the root. And so when we have the turbulent flow of a stall, the control surfaces become in the turbulent flow of a stall, the control surfaces become less effective. So airplanes are designed this way with the shape and the twist of the wing because it is advantageous that the stall occurs the furthest away from the ailerons, allowing them to remain effective in the stall. So if we were to stall out by the ailerons, we wouldn't be able to control them as much, and therefore we wouldn't be able to recover as well. So that's why they've designed the aircrafts the way they do to stall at the wing root instead of the tips. And so to recover and prevent a stall, we must reduce our attitude immediately to get below that critical angle of attack and gain airspeed and flow over the wings again. And this is done by pitching down. So the first thing you want to do is pitch down to break that critical angle of attack. Then the other parts of the recovery process depends on if you are in a power on or a power off stall. And so for a power off stall, this is going to be simulating a landing stall. So typically you're going to have full flaps and you're going to want to disconnect the autopilot and assume manual control if applicable. I personally don't use autopilot at all when I'm doing any maneuvers. I don't think I know most people that do, but if you are using the autopilot for some reason, disconnect it and just manually fly the airplane. Reduce your attitude immediately to get below the critical angle of attack and gain airspeed and flow over the wings. And if the aircraft's power is idle, you want to immediately add full power in at the same time. So as you're pitching down, you're going to want to slowly add full power to break that stall and gain airspeed. And if the aircraft's wings are not level, you want to level them as well. So simultaneously, you're going to want to reduce the angle of attack, slowly add power, and slowly and level the wings if you were in a bank. And if your flaps are deployed, you're going to take them back in increments to the neutral position as you gain enough airspeed. So typically, when I've recovered from stalls, the first thing you do is you pitch down, you add power, you get level if you're not already, and then you slowly start to take away the flaps, make sure that you're gaining airspeed. And before I put my last notch of flaps up, I make sure that I have a positive rate of climb and I'm at a safe airspeed to do so. And typically in my aircraft, it's around 70 or 80 knots, but you just want to have that positive rate of climb and then slowly retract the last set of flaps to neutral. And then in a power on stall, this is going to be our stall that's simulating during takeoff. So like this would be like the stall you would see like if you were taking off. So again, you'd want to disconnect your autopilot, assuming if you had one. You'd want to reduce your attitude immediately get below that critical angle of attack and then gain airspeed and flow over the wings again. And you want to make sure that you're also wings level. And obviously, you're going to have full power already in, and then you're just going to want to build up enough airspeed. And then once you have sufficient airspeed, you're going to pitch up again and have a little bit of a climb and then level off as needed. Is there any questions on stalls, load factor, stall recovery so far? I know it can be kind of a lot. Okay. So now we're going to talk about a tailplane stall. And tailplane stalls, so we have the horizontal stabilizer here, or that can be viewed as a miniature version of your wings, and it sometimes is called the tailplane. So just like your wings, the wings of the tailplane, or your horizontal stabilizers with your elevator control surfaces can also stall in what we call a tailplane stall or a tail stall. And a common cause of tail stalls is the accumulation of ice on the tail surface. And so usually the tail accumulates ice first and faster than the main wings because the edges are smaller and sharper, and its placements on the aircraft is in position more subject to the weather conditions. And typically, if you are going to get ice, it starts to accumulate on smaller parts of your aircraft first, and then it'll start to accumulate on the bigger parts of your aircraft. And so with the tail, the most common is on high wing aircrafts on approach with flaps and extended and icy conditions. and the situation is difficult to detect because you cannot see the tail surface from the cockpit. And tailplane icing can be detected by a sudden change in elevator force or uncommon nose down pitch. So you might be pushing down or back on your elevator, and you might feel that you might not have as much control as you normally would if you didn't have ice on your aircraft. And so then the tail stalls are considered more dangerous than a normal wing stall because they are difficult to detect. So there's no stall horn here, and there's an onset. The onset is abrupt, so it's going to happen fast, and you're not going to be able to notice it. So that's why these are the most dangerous types of stalls. And for me, anytime you're flying when it's in colder weather, you always want to make sure that you are checking the freezing level, checking the icing levels, the icing charts on like aviationweather.gov or ForeFlight before you go out and fly, because majority of general aviation aircraft, unless you're flying like a Cirrus or something super fancy, they are not rated for known icing conditions. So just make sure before you go fly to check the weather, check the temperatures out, check the freezing levels, because you do not want to get into a situation like this. Because if you have like a tailplane stall, they are very difficult to recover from. So you just want to make sure that you're doing your proper pre-flight planning before you go out and fly. Any question on tailplane stalls? Okay. Next, we're going to talk a little bit about T-tail aircraft. So these refer to aircraft that are designed to put the horizontal stabilizer and the elevator on the top of the tail, creating a T shape. So as you can see here with this jet, we've got a little bit of the T shape here going on with the T-tail. And this puts the elevator above the effects of the downwash and spiraling slipstream from the propeller. In a jet engine aircraft, the T-tail design is even more popular because it helps the tail avoid the exhaust blast of the engines. And as you can see here with in terms of a stall, a T-tail aircraft is more susceptible to entering a deep and more dangerous stall at a higher angle of attack and low airspeeds. And this is because at a very high angle of attack, the wake vortices of the wings encompasses the T-tail, making the elevator almost completely ineffective. So as you can see here, like the vortices and being at a high angle of attack, it's hitting the back of the T-tail here and making it pretty ineffective to control. So that's why it's very dangerous, especially like in a jet, like a T-tail aircraft to stall in, because you might not be able to recover from it. Is there any questions on T-tail aircraft? All right, so next we're going to talk about spins and what the difference between a spin versus a spiral is. So a spin is a stall with auto rotation about the vertical axis that is caused by a stall plus a yaw simultaneously. An aircraft spiral is a steep descending turn in which the airplane's nose drops and its airspeed rapidly increases as it continues to lose altitude in a tightening spiral. The difference between the spiral and the spin is that there's no stalling in a spiral. The critical angle of attack has yet to be exceeded, and the wings are still receiving attached flow. But with the spin, the aircraft is in a full stall, not a partial stall. The stalls on either wing are asymmetrical, and a spin can be entered from any flight attitude and from almost any airspeed. And this is a visual representation of a spin. And when you are spinning the aircraft, if you are going to spin an aircraft for whatever reason, make sure that it's in an airplane that's rated for it, and make sure that you're going up with an instructor who's qualified to do this. You typically won't do spin training in primary flight training. You typically do this once you go to CFI. So when I was in CFI, like I had one spin flight and it felt like it was crazy. Like I don't know if it felt like this, but we were doing them over the ocean because I was in Florida, and like I accidentally looked down, and that was like the only time I felt kind of sick in the plane because you feel the G's so much when you are spinning, and it is like crazy. But the airplane inherently, most GA aircraft are inherently stable, so they don't want to spin. So you actually really have to manhandle these things to spin and have to put it in some crazy maneuvers. And I do remember from CFI training, like if you failed spins or failed teaching spins on the check ride, you'd have to take an airplane that was rated to spin and perform a spin for the examiner. So luckily I didn't have to do that. So, but yeah, it's really wild. It's a fun feeling though, like, but it is definitely a lot more like G-force than I thought it was going to be. And it is very hard to get it into a spin. Yeah, it'd be wild for spins to be common. It's probably because, Mark, it like some people like, you only get introduced to spins like the acknowledgement of like, spin recovery because, majority of general aviation aircraft aren't rated for spins. And I think that's why they don't have you spin on the commercial check ride, but you don't have to spin on a private check ride for sure. You just have to know how to recover from a spin. And we'll get to that in just a second. So we're going to bring back our base to final turn again as another example for spins. So this is another common area for a pilot to get into a spin as well as just a normal stall. Unfortunately, this usually ends up in a crash due to the average spin recovery needing up to 1,200 feet of altitude. When you are low and slow, you want to avoid uncoordinated turns at all costs. So when I went up for my spin flight, we went up to 6,000 feet AGL and we spun there. But yeah, it does take about 1,200 feet, sometimes even more to recover from a spin, depending on how aggressive the spin is. But yeah, you do lose a lot of altitude when you're trying to recover from a spin. So that's why when we do demonstrate them, they are pretty high up. And then another time it could occur is after takeoff and the pilot's trying to make a hard bank either to return to the airport or for an emergency. And with back to the airport, that would be that impossible turn like we talked about earlier. So making that impossible turn, you could already be stalled and then you're already stalled and then you try and bank harder, then you're going to just spin the aircraft. And so with spins, all we really care about here is the recovery from the spins. And so if you, for whatever reason, were in a spin, you'd have the stall that occurs when you're at the critical angle of attack, so at the top here. Then the wings are stalled, and thus the flow over the wing is separated, and that means the ailerons are not as effective as in a normal flight, and the nose drops, as you can see here with the plane here. And then after that point, the stall causes nose to draw to yaw, and the yaw and the stall asymmetry causes the auto rotation. And so to recover from a stall, we will use, if you're in a high wing aircraft, you'll use the acronym PARE, which P stands for power, and that means you're going to immediately reduce your power to idle. And the asymmetry of the stall and the yaw causes the auto rotation of the spin, and the power from the aircraft's propeller is aiding in the rotational speed of the aircraft. Therefore, the first thing the pilot should do when they realize they are in a spin is to reduce the power immediately because we want to stop the rotation of the aircraft. The next thing you're going to want to do is level your wings. So A is going to be for your ailerons. You're going to want to level your wings with ailerons neutral. And this, with neutralizing the ailerons, meaning to center the yoke with no left or right input, a pilot should not try to bank or use ailerons to recover from the spin because it can just make the spin worse. So that's why leveling your wings and neutralizing your ailerons is good because we're trying to break that spin, break that rotation. And then with the R here is rudder. So what you're going to do is you're going to put full rudder against the direction of the spin to combat the rotation of the aircraft. So if I'm spinning to the left, I'm going to want to use right rudder to stop the direction of the spin to combat the rotation of the aircraft. So you're going to use full rudder to the floor. And then E is going to be for your elevator. And you're going to use your elevator by pitching down to gain airspeed and recover from the stall. And this will reduce, and with this, you're going to reduce your rudder input once the spin has stopped. And then for recovery, once you're at a safe airspeed is reached, then you're going to add full power and climb out at VX or VY, whichever is appropriate. And ultimately, a pilot should always consult their aircraft specific stall and spin recovery steps because it also differs for every aircraft. But for most training aircraft, PARE can be helpful. But in just a second, we're going to talk about if you were in a low wing aircraft. So the PARE applies if you're in a high wing aircraft like a Cessna, but if you're in a low wing aircraft like a Piper Archer or a Cherokee, you're going to use what's called REAP. And REAP is going to be rudder opposite first. Then you're going to have elevator, pitch down to gain airspeed, ailerons, neutral, and power idle. It's essentially PARE, just backwards a little bit. So a little bit of a similar steps for a low wing. It's just a little bit opposite versus the PARE, which is going to be power back, ailerons, neutral, rudder opposite, elevator forward. So, any questions on spins or spin recovery? Nope. But you probably won't spin the aircraft in private. If you, for some reason, decide you want to become a CFI someday, you will have spin training. But typically, you're just gonna, what you need to know at this level is how to recover from a spin and what causes a spin. But just the awareness of it, you're not actually going to perform this maneuver. Hopefully, none of you perform this maneuver because it is quite dangerous and it is not a good feeling to be in a spin, let me tell you. I mean, it's fun when you're doing it purposefully, like I was in training, but if you get yourself into something like that, it is really dangerous. So next we're going to move on. We're going to talk about weight. So this is our downward force of gravity on a certain air mass, and this in this mass, for example, is our aircraft. And the aircraft's mass times the gravitational constant gives you the force of weight downwards caused by the aircraft's mass and Earth's gravity. And the center of gravity, or the CG of the aircraft, may be considered as a point at which all the weight of the aircraft is concentrated. So if we had an aircraft where, if an aircraft were supported exactly by its center of gravity, it would be perfectly balanced. And as you can see here, the center of gravity is typically in typically forward a little bit more depending on the aircraft's designers, but this is where the center of gravity is in this example. So if I were to take a string and put it on the top of this aircraft, it would balance at this point of the aircraft here. So, and we'll get further into center of gravity when we talk about weight and balance, but this is where the aircraft is balanced. Yeah, and I like Nick's example too. So think of a pencil on your finger. The point of the pencil where you get it to balance is the pencil's center of gravity. Yeah, or like if we took a string and we hung it off the airplane and we just watched it balance like it was like an ornament or something, you could see like it would balance at this point here. Sir, is there any questions about weight or center of gravity? Okay. So I was thinking, since we're going to move into another topic and we're almost at 8 o'clock, if you guys want to take a break early or if you guys want me to keep trucking along. Coffee break. Okay, Mark. All right. So we will take a 5-minute break. I have 7:54 on my computer or 4:54 Pacific time. So why don't we come back at we'll come back at 8. How's that? Or 6. Or no, it would be 5. 5 Pacific. So 8 p.m. Eastern. 5 p.m. Pacific. Hi, hopefully everyone had a good break. Give it another minute.
Well, yeah, that's the time to stretch, move around, refresh yourself,
Yeah.
get
No,
ready
yeah.
for another hour.
Yep. Exactly. All
Hey,
right.
Nick. Oh, sorry. Never mind. Go ahead.
Oh, you're good.
What's up?
Um,
No, good, good. It was just a side comment about the in your picture you showed an example of a beach craft tomahawk in one of your pictures,
Oh yeah.
and in short version, I get winded, but short version, 84, I was attending my chemical officer advanced course, Anniston, Alabama, and I found an instructor down there, and they had a beechcraft tomahawk as the bird to fly in. So we went up a couple of times, and so we would go up to like 8,000 feet at AGL, and he showed me spin training, and that scared the holy blank out of me. Now this is a military, he was a military pilot, but all I'm saying is the nickname for that instead of a tomahawk was called a terror hawk.
Oh,
That's what he called it, a terror hawk. Anyway, side note, back to school.
no worries. I love it.
let's see, Rob, will you be going over how to calculate load factors? Um, I'm pretty
No.
one.
You won't. I don't think there's a question. I'm kind of looking right now on the course to see if there's a question. Dude, I don't think we ask you to, and I don't think the FAA written will ask you to do that.
Yeah, I don't think
I
so either.
I know they have those graphs that relate it to like an increase in stall speed. They might ask you to say how much did this increase. It was on one of your slides. Do you mean the equation for load factor?
Yeah, that one, unless I'm thinking it's like they'll show you like a chart like this.
Yeah, that one.
Yeah,
Yeah, yeah,
so
yeah.
so this isn't like an equation, but they'll just be like, okay, at what angle, like if you're at a bank of 60 degrees, like what's your load factor? So then essentially you have to go on the chart and say, okay, well, if I'm at a 60-degree bank angle, my load factor is going to be 2.
I was looking. I was going to take one of the tests, and it said, "What if your aircraft weighs 2,300 pounds? At what point?" Uh,
Yeah. So okay, I see what you mean. Yeah. So in that example, you find the load factor. So in Ali's example, say 60-degree bank angle, load factor is 2, just to make it easy. Uh, the the load that you would feel, or what they want in the question, is just the load factor or the G forces times your weight. So if they give you a weight of 2,300, if you have a low G force of 2, it's 2,300 times 2. So it'll give you
4,600. Yeah, yeah.
4,600. Yeah. So it's
Sorry.
it's what you feel. The weight you feel is what you would calculate in that. Does that make sense?
it does. I was taking, I think it was the stalls quiz, and then that popped up by like the third or fourth question. Then I stopped taking the quiz because I don't know how to calculate those.
Right. Yeah. I kind of forgot about that one, to be honest.
There's a
So
couple
good,
of them in there I had to
good.
stop and say, well, I'll go back and might be on tonight's lessons.
Yeah. Yeah. That's a good question. Maybe we'll do a couple examples on Friday after you guys give it a try in the quiz.
Okay.
Hmm. Yeah, I'll make note of that for Friday.
So I'm sure those are going to be some of the questions that would probably come up on the written, FAA written, how to do this.
Yeah, I think I remember I got one like that. They're pretty easy, like once you figure it out. They throw the graph looks intimidating, but it's really not. Like you just line it up and then you take your load factor and you times it by your weight. And yeah. Okay, and then John says there's 3 different questions on the quiz like that.
Yeah,
So
can you
yeah,
just
we can practice those on Friday too.
okay.
Yeah.
Yeah, so if we just real quick, I know we got time, but since it is on the quiz that they have to do, I feel like we should show them. Um so if I can I take over real quick? I just want to
Yeah, yeah.
do another example real quick.
Yeah, of course.
Um all right, so share this here. Can you guys see that?
Yes.
Yep.
Okay, cool. All right, so let's say, does someone want to tell me what, John? I think you were looking at the questions. Do you want to tell me one of the questions?
The one that Rob was talking about also, and then there's another one that says something about if you're, I think if your plane weighs 3,300 pounds or something, but you had to, I forget what you had to calculate, but there's three different ones you have to use, some type of formula to, one you have to use the square root of the G force, and then I can't remember what you have to do with that. I think you have to multiply it back in or something like that. But
You said it was in the stalls quiz.
yeah,
Okay,
28
let me.
quiz, yeah.
Okay, so I see okay, I think, is it this one? If an airplane weighs 3,300 pounds, what
yes,
approximate weight would the airplane structure be required to support during a 30-degree bank turn while maintaining altitude?
exactly.
Okay.
Okay.
So 30-degree bank, and it weighed 3,300 pounds.
Yep.
Okay. And it's asking, what weight would the structure need to maintain? So basically what it's saying is that straight and level flight, when our G forces are 1, the weight of the aircraft, the structure needs to support a 1G weight. So 1G, so the weight 3,300 times 1 is 3,300. Now, if our G forces go to 2, the weight, the force of weight that our structure needs to be able to hold is 2 times our weight. So it would be 6,600. So what you do is just like we showed before, you look for 30 on this chart here. On the FAA written, the figure that the FAA written gives, they also give you a table on the side. It's the same value. So if you don't want to look at the chart, you can just look at the table. It's like they tell you like bank angle of 10, 20, 30, and then they tell you the actual values of load factor. They say like 0.3, 1, 1.2 or whatever. So you can use a table and you can interpolate, or you can just use this and kind of eyeball it. Obviously, the table helps for some of these lower ones where it's really hard to see how far above 1 it actually is. So either one works. It's the same information though. So let's say we're just going to use this here. So 30, I'd say it's about like 1.1,
I've got
right? So
the figure here, like from the table if you want that too.
That'd be great.
okay. All right, let me pull that up. What figure number is it?
Figure two, but you were on it with like the 1.1.
Let me just pull it up so everybody can see that.
Yeah. And like this is a lot easier, and it looks just like this on the written too for the table with the chart. Um,
Yeah, it's the same figure.
mhm.
Let's see here. Figure 2. All right, there we go. Figure 2. Let me pull that up for you guys. All right. So let me just erase something here. Okay. So yeah. This one. So 30 degrees. It's 1.15. You could also just look here and eyeball it. It's like 1.1, 1.15. So 1.154 is what we're going to use. And we just simply multiply 1.154 times 3,300. And let's do this calculator real quick. 3,300 times 1.154 equals 3808. So that's the amount of weight your aircraft structure would be able to support during a 30-degree bank turn if your aircraft weighed 3,300 pounds.
Okay.
Any questions?
No, that makes sense.
Okay. John, you said, Allie, you're looking at the questions. John said there was one about a square root.
Yeah, I'm gonna look for that one too. Let's see.
I think it was a square. It was calling for 2Gs, and you had to get the square root of 2.
Okay, let me see. What is the approximate stall speed during a 2G load factor bank when the aircraft straight and level stall speed is listed at 50? Is that it?
I believe that's correct.
Okay.
You want to?
Yeah, I'm gonna pull it.
Okay.
I'm gonna put it in the chat.
Okay, thanks. What is the approximate stall speed during a 2G load factor bank when the aircraft straight and level stall speed? Does it give a figure number?
Let me go back and see. No, it doesn't.
Okay. What is the approximate stall speed? I'm trying to figure out where we were going with this 2G load factor. I'll let you continue, Allie, and then let me look into this. I just want to make sure
I
don't go about this the wrong way.
You're
I'm gonna
good.
take a look at it on my end. And then
like I see the notes, but yeah, like that's good. Let me get back to sharing my screen. All right, can everyone see my screen again? Perfect. All right, so we're going to move on now, and we are going to talk about thrust or power. And this is going to be our forward force, and this is the force on the aircraft that opposes drag. And if thrust is greater than drag, the aircraft will accelerate, so a positive change in airspeed. And if the thrust is less than drag, the aircraft will decelerate or a negative change in airspeed. And so thrust is the green arrow on our 4 forces here. And as you can see here, if thrust is greater than drag, the aircraft will accelerate, and if it's negative, it'll decelerate. But in straight and level unaccelerated flight, an aircraft's lift must equal its weight, thrust, and so in straight and unaccelerated level flight, lift must equal weight and thrust must equal drag. And pilots add thrust by adding power and increasing the RPMs on their tachometer. And in each of these cases, you are targeting a safe airspeed and will be taught to pitch for airspeed and change power accordingly. The two always work incoherent with each other. So if you've ever heard like your instructor or someone say pitch, power, trim, so you want to pitch for the attitude you want, whether that's straight and level flight, whether that's descent, whether that's a climb, you want to pitch for that first. So once you have the attitude that you want, you keep it at that pitch. Then you're going to add power to maintain that. So you're going to add power to maintain whatever power setting you need to maintain straight and level flight, whatever power setting needed for a climb or a descent. So in those cases, you may be adding or taking away power depending on, the conditions for the day, that sort of thing. So you're going to add power to maintain that position. So that's where the word power comes into play. And then with trim, remember, we are using trim to relieve the control surfaces from ourselves or the pilot. So you're either going to add nose down trim or nose up trim, depending on if you're in straight and level flight or descending or climbing. So whatever you need to maintain that, you're going to add trim as necessary. So anytime you go from straight and level flight, you're going to need to adjust your pitch, your power, and your trim. So that's just three big things you're just going to want to keep adjusting all the time in flight. So unless you're staying at one position, so unless you're flying straight and level the whole time, you're going to need to make those pitch, power, and trim adjustments accordingly in order to maintain that position that you want. And the relationship of power and the aircraft pitch attitude is a key concept you'll need to learn during flight training. Like I just said with the pitch, power, trim, that's just something that you need to have, down, especially when you're first starting out, because, you want to make sure that you're able to maintain the aircraft's position depending on, the setting you have. So you may need to add or take away power depending on if you're climbing, descending, or in straight and level flight. And the conditions one day might differ the next day. So the power setting you had that day for, straight and level flight might be different the next day based on, density, temperature, all that stuff. So just making sure that you really get pitch, power, trim down is so important. And for every aspect of flying, there is a pitch, attitude, and a power that works in tandem. So, for example, we have when you're taking off, you will usually pitch to somewhere around 15 degrees with full power. When you're landing, you will also have a positive pitch attitude in order to slow to your approach speed. And you'll also have a condescending power, coinciding power, usually about 60% or less of full power. So usually when I'm taking off, I pitch to roughly about 10 degrees is what I can hold roughly about 70 knots when I have flaps in. And then once I take away the flaps, I'm usually about 75 is what I like to climb out at once I have a positive rate of climb in my aircraft. And then when I'm coming into land, I have that positive pitch again, but you just want to slow your approach speed so that you have about 60% or less power depending on the day. Sometimes you may need more power, some days you might need less power. It all depends on how your approach is and all that. So, um, let's say you're landing and you're trying to target an approach speed of 70 knots, but you are still a little fast at 75 knots. So you decide to pitch up, but you decide to pitch up too slow to slow down to 70. If you do this without adding a little bit of power, you may start descending much faster than you would like and below the glide slope in no time. So to stay on your glide slope, you'll just add a little bit of power after pitching up to slow down. So you just want to, so in this instance, instead of like, yeah, you can, pitch down, but if you don't add the power, you're going to be descending too quickly. So you need to, whatever power setting you need in order to maintain glide slope, use it, whether you need to add a little bit of power, take some power out. But in this example, you need to pitch down and you need to pitch down to slow down to 70 knots, but you need to add a little bit of power so that you can descend because without adding a little bit of power, you may descend too fast. So you just want to have enough power in order to maintain your glide slope. And we'll talk more about glide slope and all that when we get to landing, but it's just so crucial to have good power management when it comes to, flying straight and level, when it comes to taking off, landing, that sort of thing. And that's where pitch, power, trim really comes into play with thrust. And so consider you're flying straight and level with 70% max power, but you decide to add full power. What's going to happen to the aircraft if you do not do nothing? So let's say you add 70% of your power, but you decide to add, you're at 70%, but you're going to add full power. What do you guys think is going to happen to the aircraft's attitude if you do nothing else? We've got a couple that are saying climb, pitch up, turn left. Yeah, so the ones that said climb, pitch up, yeah, the aircraft's airspeed is and the ground speed will initially increase, and the increase in airspeed is going to increase your angle of attack. So from our previous lesson of the lift, we know that increasing speed and angle of attack both increases the lift on the aircraft, so the aircraft is going to want to climb. So if a pilot desires to climb, nothing needs to occur. But let's say you added power and you just wanted to maintain straight and level flight. Well, now if you don't do anything, your airplane's going to slowly start to climb up. And so it's really important as pilots, if we added power and we're straight and level, you have to trim for that new air, you have to pitch for that new airspeed. You have to add power for that airspeed, that setting, and you need to trim for it. So if you added power in that instance, you have to trim for straight and level flight. So you may need more nose down trim in this instance so that you don't climb. But if you wish to remain straight and level, you need to have a lower pitch. So you need to pitch down a little bit, and then you already adjusted your power, and then you just need to trim accordingly to convert that added energy into airspeed. So it's just really important to make sure when you're adding power, if you're in straight and level and you want to remain you want to climb, that's fine because you're going to climb. But if you add power and you're in straight and level flight and you didn't want to do that, you're going to slowly start to climb and it'll creep up on you a little bit when you might not even notice it right away if you're not paying attention. But that's why it's so critical to pitch for the attitude that you want, add power for what you need to maintain that, and then trim accordingly, so that you are doing what you need to do. So any questions so far on thrust? It is important to remove the trim before climbing in. You don't need to remove the trim, Mark, but once you are climbing, you may add like a little bit of nose up trim if you know you're gonna climb. But like first, it's just you would pitch up for your climb first, then add power, and then once you've added your power, then like what I like to do is I kind of let go of the yoke a little bit. I mean, I still have like control of it, but I just kind of see, okay, where's my airplane going? If it's going to continue to nose down, then you're going to want to add a little bit of nose up trim. So after you've done your pitch and your power, you just kind of like look and see, okay, is it maintaining that climb attitude that I want, or is it pitching back down? And so then adding, in that case, if the nose was pitching down, adding a little bit of nose up trim to help keep it in that climb is going to help. But you don't need to remove trim before you climb again. Hopefully that answers your question. Okay, good. All right. So now we're going to talk about the last force of flight, which is going to be drag. And this is the opposing force of thrust, and that's called drag. And that's our rearward force. And we've got another equation here for you guys, but don't worry, you guys don't have to memorize this. But this, similar to how we have the lift equation, we have the drag equation, which is pretty much the same thing. Now we have the coefficient of drag instead of the coefficient of lift. And so that's what this equation is. So drag is equal to the coefficient of lift with the density and the airspeed or the velocity squared, and then we have the surface area of our wing over 2. And from the equation above, one can notice that the density, velocity, and the surface area affect drag in the exact same way that it affects lift. And so we have this figure here with our chart. So we had a chart that showcased how lift increased with the angle of attack and linearly with the critical angle of attack. Well, if drag also increases with angle of attack, but it does so in a more parabolic shape, such that it is certain that there's a certain angle of attack where the difference between lift and drag is a maximum. And this is an important point to know, as this is the most efficient place to fly. We call this the maximum lift to drag ratio, or the maximum lift over drag. If we fly at our aircraft's maximum lift over drag ratio and the angle of attack that gives us that ratio, our aircraft will have a maximum range and glide capability. So this green line here represents our maximum lift over drag. So this is where we're going to get our most efficient flying out of. This is equation, not equation, this graph also gives us our best glide speed. So our best glide speed would be the best speed at which we would glide our aircraft for, particularly when you're in an emergency situation, when you're running your checklists, you're pitching for best glide because that's what's going to give you your maximum gliding distance, that best airspeed for that. And with drag, there's two major types of drag. We have our parasite drag and we have our induced drag. And with our parasite drag, we break that down into three types of drag as well. We have form drag, interference drag, and skin friction drag, which we will talk about in just a second. But remember when we talked about the laminar flow over the wings and how the air stayed perfectly attached to the wings and contoured to the wings shape? Well, anything that disrupts the laminar flow is drag. And in this example, we have form drag. And form drag is a type of parasite drag. So as you can see, form drag is based heavily upon the shape of an object. So as you can see, we have a rectangle here, and the shape of this rectangle has large turbulent flow behind it. So it's not a very efficient form of flight object because of the laminar flow and the large turbulence that we get behind it is very disruptive and it doesn't smoothly flow in the air. Then we have our sphere, and with our sphere, we get a little bit better efficiency. We get smaller turbulence, so we don't have as much as our disk or our rectangle here, but we also, could be a little bit better as far as like our turbulence and our wake behind us. But with our teardrop or the shape of our airfoil here, we have our smallest turbulence. So when aircraft manufacturers are designing aircrafts, they take form drag into consideration when designing like the shape of the wings, the shape of the fuselage and the empennage, that sort of thing, so that we get the least amount of form drag.
Yeah, so I like to think like if you're driving on the highway and you stick your hand out of the window and you have it, flat into the wind, it's going to be like that disc, right? And it's going to want to push your hand backwards. But then if you were to tilt it, like this, tilt your hand like this so that it's, palm down, you're kind of like that tear shape and you'll be able to hold your hand in that wind a lot easier. Also, whenever you hear of like, oh, that car looks aerodynamic or that thing looks aerodynamic, what people are talking about is really it has low form drag. The shape of it is such that it's reducing its form drag.
Mm-hmm. Yeah. So next time you're like in the passenger seat of your car, when someone else is driving, like stick your hand out the window if it's safe to do so and practice that, practice with the hand stopped like this and then like with it like this. So you can really feel the effects of the form drag around your hand. Next we have what's called interference drag. So we have the free streaming air from our propeller, and there's intersections around the wing edge, and the slipstream here that we have, and that causes drag because of the intersections along the wing and along the fuselage of the aircraft. So we get this little bit of a slipstream here. So that's the interference that we have with the aircraft with that type of drag. And so with aircraft manufacturers, instead of like them making the aircraft wings like a hard stop right angle here, they try and curve it and make it a little bit smoother around the wings edges and those types of places so that the effects of interference drag are lessened so we don't feel it as much. But anytime you have like wind flowing over an object, if it's not like smooth and it has like hard, sharp lines, it's not going to the air is not going to flow as smoothly over it as it would if it was a little bit rounded, a little bit more curved. So aircraft manufacturers take this into account when they're designing the aircraft, so that way we don't have as much interference drag from that and causing that slipstream effect. And then the last form of parasite drag we have is called skin friction drag. And this one, as you can see here, we have the top. This is the top of our airfoil, for example, and this doesn't happen at just the airfoil. It could happen at any part of the aircraft, but there is little microscopic imperfections in our aircraft. And what happens is these little black dots, which are the free stream velocity or the air molecules, they start to stick to the aircraft surface, and that causes drag. And so what happens is aircraft manufacturers, they try and do this based on, they try and like get, we're never going to 100% get away from skin friction drag. We're always going to have a little bit of it. But the best ways that you can keep like this from happening is like having your aircraft like inspected, getting specific paint that's made for airplanes. That's why paint's like so particular for aircrafts, because of like having skin friction drag like kind of taken out of it. But we're always going to have like little imperfections that we can't see with our eyes with skin friction drag. And so these air molecules just stick to the surface of our aircraft in those little imperfections and cause a little bit of drag. But like the types of metal that they use and the paints that they use and that sort of thing helps to decrease skin friction drag. But we're always going to have like a little bit of it, depending on like, if there's a little imperfection or not.
Yeah, and Mark had a question, would flying banners on aircraft be considered parasite drag? Yeah, so when you're towing a banner, not only do you have the added weight that you have to tow, but also the banner is going to have some amount of form drag. Obviously, it's like skinny flying, so depending on what direction you're going, it could, against the relative wind, the form drag could be small, but it's still going to have some. And then it'll definitely have skin friction drag. Interference drag, there could be interference drag as well. There could be all bits of drag, but yeah, I think it would mostly be parasite drag. And then yeah, frost increases, it ruins that smooth paint job that we really want. And we want our flow to flow laminarly, the airflow to flow laminarly over our wings. And so the tiny imperfections on the surface or ice or frost can ruin that flow, cause our boundary layer to increase or turbulent flow over our wings, which increases our drag.
Yeah, and same good thing there, John. Even on completely smooth surface, you can have peaks and valleys. Yep.
Yeah, have you guys ever seen like sometimes I'll see it online. It's like, something that's to us, it's like super smooth. But if you look at it in a microscope, it looks like, the Himalayas, it's like, that's what's going on. And so to us, when our thumb goes over, it feels really smooth. But to tiny air molecules, when they're real close to it, it's literally like going over the Himalayas. So they're gonna have to go up and down, and they'll get stuck, and then they kind of get, when they're real close, they get bunched up. There's traffic because they can't just flow in a smooth line. But as you get further and further away from those imperfections, where we show that free stream velocity, there's like no traffic or whatever, because they're not affected by the friction anymore.
Oh, nice, John. And so the last drag we're going to talk about, so we just wrapped up our parasite drag. So now we're going to talk about induced drag, and this is the last type of drag that we have. And so induced drag is the drag that's caused by lift, or it's a byproduct of lift. Although the aircrafts are designed to produce as much lift as possible, this lift comes at a price, which is induced drag. So the more lift that we create, the more induced drag that we have. And so in this example here, remember when we discussed how lift was created by turning off the turning of the free stream flow and the creation of a pressure differential between the areas below and above the wing. Well, when we know the areas of high pressure want to reach areas of low pressure, in this case of a wing, this cannot happen directly up or down because the surface of a wing is in the way. But it can happen at the trailing edge and at the end of the wingtips where the two areas of air meet up. We get what's called wingtip vortices, as you can see here. That's going to be like our down or like our downwash. So we have our free stream flow of air. We have our high pressure and our low pressure, and they meet and converge together at the back here. And we get that clockwise rotation on the left side here. And then we get a counterclockwise rotation on the other side. So that net downwash here, that's our induced drag, and that's our wingtip vortices. And we'll talk a little bit more about that when we get into wake turbulence. But we have that high pressure air under the wings gets sucked up in the low pressure air area above the wing at both the trailing edge and the wingtips. And because of this, the flow of air tends to go towards the trailing edge and the wingtips. And this flow causes the vortices at the wingtips shown here. And as the air flows off the wingtip and it turns upwards beyond the tip of the wing before turning upside down, and to create a downwash inside and behind the trailing edge of the wing. And so we get that wingtip vortices. And here's a really good depiction of two aircraft, and their wingtip vortices. And as you can see, the vortices spin and go downwards, creating a net downwash. And this net downward force has the effect of drag against the aircraft's forward motion. And so this is what wingtip vortices look like in action and your induced drag. So is there any questions so far on drag? Okay, so
What?
now, oh,
I was just gonna say I can because you're done, right?
I thought we had to talk about wake turbulence still.
Oh yeah, sorry. Go ahead.
You're
I
good.
was gonna jump in and answer that load factor question, but go ahead, continue.
Oh, sorry. Yeah, we're almost done. So, all right. And so to tie in with drag a little bit, we have wake turbulence. So same image here with our wake turbulence. We have our vortices here that the aircraft produces. And with these vortices, we get what's called wake turbulence. And this is the more lift an aircraft generates, the stronger the wake turbulence it is. And the bigger the aircraft, the more pronounced those vortices are. And these vortices are the highest in slow, heavy, and clean aircraft. Clean just means no flaps or landing gear extended and no payloads attached to the wings like weapons or tanks, that sort of thing. So when you think of clean, like it's not like, oh, the aircraft's really clean. Like, no, it just means there's no flaps or gear or payload attached to the wings. So typically, like these types of planes, I think of like, 787 or 747, like really big, heavy, slow, clean aircraft when they're taking off. And a slow, heavy, clean aircraft happens to be the exact configuration of a large passenger aircraft during a climb out. And so, private pilots, we must be aware of when we're taking off and landing after one of these aircrafts because their wakes are pretty big. And even at smaller airports like, my Class Delta airport where I fly out of, we still have jets that come in and out of there. And occasionally we do get 7-3 traffic because one of the soccer teams, they fly into there on a 7-3 with Sun Country. And it's pretty daunting, like seeing one of those and then having to take off or land near one. It's crazy. But anyway, we'll talk more about that in just a second. Um, even turbine-powered private jets can cause considerable wake turbulence and should be avoided by those of us flying smaller aircraft. And that's why sometimes when you're flying at some of these smaller airports, you'll still see jets, and sometimes you'll hear the phrase ATC, caution wake turbulence. Well, that's because even these smaller jets, they're bigger than us, so they're going to be producing more wake behind them. So that can be pretty detrimental to us depending on the circumstances for the day. And so with wake turbulence, we want to avoid wake turbulence as pilots because when we're landing, and especially when we're landing, we want to avoid wake turbulence by avoiding it as much as possible. And so to avoid wake turbulence when we're landing, as pilots, we should touch down before the rotation. So before the wheels are off the ground point of a wake turbulence generating aircraft that has just taken off. So when we're talking about like landing, you kind of want like I think of like the bowl analogy. So like you want to land like in the bowl. So you want to land, you want to touch down before their takeoff point. So before so before that aircraft's rotation point, you wanna touch down before their point of rotation to avoid the wake turbulence, and that's depicted here. So you're just landing after an aircraft has just taken off, and as you can see here, you want to land like right before their take or point of rotation to avoid that wake turbulence. Because as you can see, you're coming into land, and they've already rotated, and so you're gonna land here to avoid that wake turbulence.
Hey, Allie, I like your bowl.
The bowl method.
Can you kind of show them what you mean? Like, so the bowl
Yeah.
would be the
Let
the
me
aircraft.
I actually have a picture of it. I want to see if I still have it on my phone.
BOWL.
Yeah, land in the bowl. There's like, let me see if I can pull the picture of it really quick. Let me stop sharing really quick and see if I can picture because I really like this method.
Well, you look up. Yeah, so basically, as we'll go through, we'll also show you how to land when an aircraft after an aircraft has just landed. So this is how to land after an aircraft is taken off. But what if an aircraft just landed? And so they kind of when an aircraft comes down to land, you want to stay above their approach path, and then when they take off, you want to stay above their approach path. So if you look at it, it's kind of like a bowl. You just want to stay above the bowl. BOWL. And Allie will show a picture of that. I think it's a good way to kind of remember it.
Yeah. I'm just like trying to see if like I still have like I don't think I have the picture on my phone. I might have deleted that one, but like I found one that kind of still from like the FAA. Let me see. So it's not like a bowl shape. It's pretty bowl shaped, but you just would want a picture. Let me see if I can draw in here. So you'd want to like pretend like there's like a bowl shape here. And so you just kind of want to stay within this bowl. So like, and we'll talk about the rotation in a minute, but like you want to touch down where their wake ends. So like right before they rotate, and then right at the point of rotation, like you want to stay like within this bowl area here. So like this little area here. Now I'm kind of mad at myself for deleting that picture. But you just kind of want to stay in that little bowl area and like not come out of it.
Yeah, I think if you keep going through the slides, it'll show each kind of individual
Yeah.
one.
Let's see. Sorry, I was trying to find like a better depiction of it.
It's okay. Here, I kind of drew one real quick.
Okay.
Share. So yeah, kind of like, so if you're coming into land and you're landing after this aircraft here has just landed you want to land after their touchdown point. And then if you're landing before this aircraft here takes off, you want to land before their takeoff point, so over here somewhere. And then if you're taking off, you want to take off after this aircraft's touchdown point, so somewhere over here. And then if you're taking off after this aircraft here, you want to take off before their takeoff point right here. So when you look at your possible, approach or takeoff paths, it creates like a bowl above, the larger aircraft's approach and takeoff paths.
Mm-hmm. And yeah, John, you can wait like usually the 3 minutes with that one. Usually, like before you take off, I would wait like 3 minutes. Like if they just said, caution wake turbulence, you can say, well, I'm gonna wait a little bit. Um, or, you can just, if you're taking off, you can take off, as we just depicted, prior after their touchdown point, which we'll talk about in just a second. But yeah, typically I would do that on takeoff. I mean, you can do that with landing too. Like you could just like, circle or wait the 3 minutes, like hold somewhere. But yeah, typically that's what I would do there. Sorry, my screen's like, I just stopped sharing for a second. I'm trying to like figure out my screen. It was like, oh, it's all funky. Yeah, with ATC, it might look a little daunting to land um in this type of situation, John, but honestly, like when I've been cleared to land and they say caution wake turbulence, it's not terrible. As long as you follow the steps. If you're coming into land, landing prior to their if the aircraft's taking off, like landing prior to their rotation point or landing after their touchdown point, it's not too terrible. I mean, there's been some times where like you can feel it a little bit if there's a bigger jet, but honestly, like I haven't really had too much of an issue with landing with wake turbulence, but yeah, it can be a bad time if like Darren's saying, if that's crazy about what happened with your friend. But yeah, if you're not doing the proper technique, it can be a bummer, but as long as you're following the procedures properly, you'll be fine. Or just waiting it out too is always a good idea as well. All right. And then, when landing, a pilot should descend above the aircraft's approach path and touch down after the touchdown point of a wake turbulence generating aircraft that has landed before them. So, like we just talked about here, so landing after an aircraft has just landed, you want to land after their point of touchdown, like we had just mentioned there. And with wake turbulence, a possible mnemonic for landing wake turbulence avoidance can be LATLB bar, or land after aircraft touchdown, land before aircraft rotation. That one's really good. I never really had a mnemonic personally for when I learned this. I just kind of remember the bowl, like stay within the bowl.
Better.
The bowl's better.
It's way better.
Yeah. So for me, I just learned, land, like if you're coming into land and they're taking off, land prior to their point of rotation. If you're coming into land and the aircraft is landing and then landing beyond they're beyond their landing point, is also good. But the bowl method I think is really good. So are you sacrificing? Okay. Yeah, you're not really, depending on where you're at, you should have plenty of runway. But yeah, usually it's not too bad. So now we're going to talk about wake turbulence, avoiding wake turbulence when we're taking off. So a pilot should rotate, so have our wheels off the ground at a point before the point of rotation and climb out above the climb out path of a wake turbulence generating aircraft that has just taken off before them. And I don't know about you, but like if it's a really big aircraft, like a 7.3 or a 7.4, thank goodness we don't really have those where I'm at, 7.4s at a Class Delta airport, but there's no way some of these aircraft, there's no way you're going to be able to like climb out of them, I feel like realistically. So for me personally, I like to just wait the 3 minutes or however long. Sometimes ATC will just hold you and make you wait if they suspect wake turbulence, if you're at a towered airport. If you're at an untowered airport, I would just wait 3 to 5 minutes. It's always better to wait than like take off and have to deal with that wake turbulence. But if it's a smaller like jet or a smaller plane, you know, if you're going to rotate, rotate at the point before the point of rotation. And if you climb out above the climb out path of wake turbulence that the aircraft before generated. And if the needed climb performance is not available in your aircraft, the pilot should avoid maneuver upwind in a crosswind from the heavy aircraft takeoff point, or just wait like the 3 to 5 minutes before you take off if you are able to do that. And this is just another visual. So taking off after an aircraft that has just taken off. So yeah, you're just climbing above them essentially. So, or just wait the 3 minutes. It's up to you. When you're the private pilot, you're going to be the PIC. But personally, if it's a really large jet, I like to wait. If it's like a smaller jet or like another general aviation aircraft, like you probably would be fine just to climb out ahead of them. Like if you think you're going to have the climb performance to out climb like their wake, um, you know, yeah, you could climb out at VX in this case to get that steeper climb gradient. So, and like your aircraft's POH, could have, obviously is going to have different VX speeds you know, depending on your aircraft. So just look at your POH for your specific VX speed. I like the 7.4 mnemonic there with the little guy. I love it. So when taking off, a pilot should rotate at a point after the touchdown point of a wake turbulence generating aircraft that has just landed. So if there's an aircraft that just landed and we want to take off, we need to rotate after the touchdown point of wake turbulence generating aircraft that has just landed. So here is it depicted again. So if we want to take off, we need to take off after they've landed. And this one makes more sense, and this one's definitely a lot more doable than the takeoff one. I would personally, just take off after their landing point in this case because you're not fighting that, wake behind you and you're not having to climb out at that, steeper angle and depending on like, you know, your aircraft performance. So you can either choose to wait the 3 minutes or you can just take off after the touchdown point. It's up to you. But in this case, I would probably, as long as your aircraft has the performance, I would just, rotate after the touchdown point for the takeoff. And then we've got another mnemonic here, which is TAAT take off after aircraft touchdown, and then take off before aircraft rotation.
Yeah, so these are the ones that I made myself when I was learning these before I heard about the bowl. But yeah, so I say like tat T bar, just I came up with whatever I could to remember all this stuff over the years, and I think it's really helpful. So whatever works for you, but throw that in there, or the bowl method, which I really like. So, but yeah, whatever works for you guys.
Yeah, I don't know what the heck I did to my screen. I like zoomed out. Okay, there we go. All right. Okay. And then with wake turbulence, the vortices of wake turbulence are affected by winds just as an aircraft is affected by winds. So if there is a presence of a crosswind in to your left, so let's say you're on the runway and there's a or there's a left crosswind, a pilot can expect the vortices of a large aircraft to be pushed to the right of the large aircraft's path. And so when the winds are heavy, the wake turbulence doesn't linger near the runway for very long because the wind pushes it away. And when the winds are high, when the winds are light, the vortices stay around longer. So with this, with this example here, if we had our touchdown point here and there's there's no wind back here, but we have the vortices here. So if we have, higher, gustier winds, the vortices will typically, if you have like vortices coming from the left, then they're gonna dissipate to the right. But if the winds are light, they're going to stay on the ground for a longer period of time. And if we have a tailwind in this case, and we just took off here with our aircraft, and we have especially like a quartering tailwind, as you can see, those vortices are going to be dissipated onto the runway. If they're coming from the left, like this left vortice here is going to come with this quartering tailwind, it's going to dissipate towards the right and stay on the runway longer. And this can especially be a problem if we have parallel runways and a crosswind, because the crosswind will blow the wake onto that adjacent runway. So even if you're taking off on a different runway, but still behind a larger aircraft with wake turbulence, you're still going to use the avoidance procedures of what we talked about earlier, because as you can see here, we have this really heavy jet. They've got these vortices here. We got this big right crosswind here. We have 27 right, 27 left. Well, this aircraft's wake turbulence is getting pushed onto 27 left here. So you're going to have a lot of you're going to have a right crosswind, but then you're also going to have this, this aircraft's left vortice be pushed into your flight path. And so in this instance, what I would personally do is I would wait the 3 minutes or however, 3 minutes before taking off, because you're battling a crosswind, and then you're also battling the vortices too. So personally, that's what I would do. I would wait before taking off. But if you did want to take off for whatever reason, you would just use the avoidance procedures we talked about earlier. So
Yeah,
in this, yeah.
And earlier we mentioned that if you can't climb, your aircraft doesn't have the climb performance to climb above the climb path of the aircraft in front of you, to turn upwind. And so if you look at 27 right, if we're taking off behind this aircraft on 27 right, what we mean by upwind is into the crosswind. So if for whatever reason you took off or something, you didn't wait the 3 minutes, and you're like, shoot, I can't get above this aircraft's climb path because this has way better climb performance than my aircraft has, then make a right turn into the crosswind to get upwind, to get basically out of the path of the vortices as soon as possible.
Yeah. So is there any questions so far on, wake turbulence or anything that we've talked about? Okay, so I'm gonna go into our last topic of the night, which is going to be ground effect. And with ground effect here, we have we have the runway between the ground and the wingspan of our aircraft. We have a net downwash of air coming off of our wing, and that creates kind of like a pillow or a layer of air. And that layer between the ground and the wingspan of our aircraft is going to be the ground effect. And so as you can see here from this depiction here, we have the prop wash coming over our aircraft, and we have our net downwash, and it's spiraling around and pushing down on the ground. And it's coming between, and it's giving us that cushion coming in with the downwash with the ground effect. So with that, we have, it's about, the ground effect starts to aid our aircraft with, so ground effect as a general rule doesn't come into effect until you're about the height above the ground equal to your aircraft's wingspan. So we don't feel this when we're flying straight and level or when we're up at altitude. We feel this when we're close to when we're about a wingspan from the ground. So at a height above the ground equal to the length of your wingspan, ground effect starts to reduce the induced drag effect, about 5% of your total induced drag on the aircraft, giving the aircraft more net lift. And at the height above ground equal to half the wingspan, ground effect reduces induced drag by about 10 or 20%. And at a height above ground equal to 1/4 of the wingspan, the ground effect reduces induced drag by about 30%. And at a height above ground equal to 1/10 of the wingspan, ground effect reduces induced drag by 50 or 60%. And so with ground effect, even a 10% reduction in induced drag can allow an aircraft to be airborne at an airspeed of 2 to 3 knots less than normal. And we need to be aware of ground effect during both takeoff and landing, because if with landing, the decrease in induced drag means that any excess speed we have on landing and approach and flare will cause a considerable floating. And if you continue like this, you'll likely lead to a very rough landing, if not one that damages the aircraft or can cause injury or go around. So in this case, if you feel that you have excess speed, and when you're coming into land and you're with your landing and your flare, it's going to cause a decrease in induced drag in your excess speed, and it's going to cause you to float, and you could potentially run out of runway. You could potentially damage the aircraft if you float too long. And in this case, just go around. If you feel like you're very fast and you feel like you're floating too long, you're running out of runway, just go around. It's easier to do that than to try and fix excessive floating. And when you have considerable floating and a ground effect, there's too much speed is to blame. So that's why you always want to make sure when you're coming into land that you manage your airspeed properly, so you're not too fast, so that you have that ground effect with a decreased in drag with the floating. And in a takeoff with ground effect, it's most likely to result in becoming airborne before reaching recommended takeoff speed. And it may seem as if you are able to fully take off in ground effect, but you can't attempt to climb out of ground effect prior to reaching an adequate airspeed, or your aircraft will initially lift off in ground effect, but then experience a reduced performance as it continues to climb out of ground effect. And this is because of the return of induced drag as you leave the ground. You will then require either more power or more airspeed by pitching down, but since you are taking off, your power will be at a maximum, and therefore pitching down and losing altitude is your only chance at not stalling. So just making sure that before we take off at our recommended rotation speed. And this is especially noticeable too, like your aircraft is going to want to sometimes take off before reaching its recommended takeoff speed, especially when we're doing like performance climb outs, like when we're doing short field takeoffs and soft field takeoffs. So it's just so important to make sure that we rotate at our rotation speed before getting airborne, not getting airborne too fast, because we could potentially stall in this instance. And here's a good depiction of ground effect. So as you're taking off with the ground effect, it decreases induced drag with the takeoff, and then your airplane may fly at a lower indicated airspeed. And then when you lift off, you want to accelerate in ground effect to at either Vx or Vy. Then when your ground effect decreases, it starts to decrease quickly with height, and then ground effect is negligible when the height is equal to the wingspan. So here. So we use ground effect to our advantage to gain airspeed, gain momentum. And then once we are, climbed out appropriately, it's not going to be negligible once we're more than one wingspan off the ground.
Yeah, so the if you could just go back to that. The key for ground effect is that we have induced drag. Induced drag is caused by the vortices that are coming down off of our wings. They kind of pull almost like you were to tie a weight to the back of your aircraft. It kind of pulls you down a little bit. It's a side effect of lift. You can't get lift without it. But some aircraft, more advanced aircraft, will do some things to dissipate that. Like if you see winglets on Boeing aircraft, or those little at the very tips of the wings, those are to reduce the wingtip vortices, to reduce that induced drag and get more. Even just a 1% reduction saves, these airlines millions of dollars in fuel. So anyways, what this figure is showing is that you can take off before your rotation speed because of ground effect, or before your climb speeds, right? Or before your stall speed. And so, but you want to be careful and understand that you're only able to do that in ground effect. So if you pitch up and you're still slow, but you climb out of ground effect, you're then going to stall because you don't have enough speed. So if you do take off too early by utilizing ground effect, you want to make sure you speed up while staying in ground effect. So we, like Ali was saying, we do this for like a soft field takeoff when we want to get off the ground. Like let's say the ground's like muddy, it's like wet grass runway or something. It's kind of muddy. We want to get off the ground as soon as possible. So we'll take off as soon as the aircraft lets us, but then we'll stay just at like 5 feet above the ground. So we'll push it forward and stay 5 feet off the ground while we gain airspeed that's then safe enough to climb up out of ground effect. And then, so the video that's next, I actually pulled that up, Ali, so I can share that on my screen so we can watch it together. This video here is a recent, probably like, October 22nd, 2025. I usually don't like showing these type of things, but they can be good for to learn from. So this guy takes off, and he probably took off too early in ground effect. He was able to take off because of ground
It's
effect.
kind of lagging and it stopped.
Yeah, I stopped it. I
Oh,
stopped
okay,
it. Yeah.
sorry.
And then you can see he also then turned. So what does turning do that we learned today? It increases your load factor. It increases your stall speed. So not only did he, pitch up out and climb out of ground effect too early, but then he was trying to fly over these photographers over here, and he just lost all lift and really awful. So that's just one. The ground effect can help us, but it can also be a danger if we don't understand what it's doing. And then while I have to share the screen, let's see if there's any questions, and then I have that load factor question that I want to show you guys. That I think it was Rob's question earlier. Are there any questions on ground effect or wake turbulence?
Let's see. Would it be fair to think of ground effect as buoyancy in water?
So a lot of people learn that it's like a cushion. It's really not a cushion. It would be more so like, man, how do I put this? Like, having, man, I don't know. I mean, yeah, you do get some buoyancy from it, but that's not 100% physically what's happening. It's really the reduction in that force that's pulling you down, the induced drag. Your vortices hit the ground and they dissipate. The ground like kills the vortices, and so you get less pulling force when you're close to the ground. it's so easy to think of it as buoyancy because you're thinking about it the right way. If you get more buoyancy when you're by the ground, but
Mhm.
technically speaking, that's not actually what's happening. But good question.
And then John said, what about tip tanks?
I don't know what that is.
That's what I was like, I don't know what those are.
The tip tanks on the end of your wings to hold extra fuel.
Oh, so what do you mean?
I didn't know if they would change the vortice or not.
Oh, oh, are you talking about like the pods that you put on the
Yeah,
wings?
yeah.
Oh, okay. Yeah, that's definitely going to have an effect on all sorts of aerodynamic stuff. I mean, you're still gonna have the vortices and everything, but it's gonna have that, more airflow will have to flow around that, and then that'll interfere with the flow, so you're gonna get more drag and all the stuff that comes with that. But you'll still get induced drag. Yeah. Okay, well, I'm gonna go back to this. So thank you for reminding me. I took some notes to add how to do these calculations in for load factor. There is one question that I forgot I added to the quiz. I don't know. We usually keep our ear to the ground on what the FAA is testing. I know it could be something you get in a check ride, so I guess I decided to add it, but I wanted to make sure there wasn't supposed to be a figure or something. But there's not, and you are right that you do have to kind of do a square root. So I want to explain kind of what's going on here. So this equation, V stall, all this, blah, 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 blah. The only thing we want to care about right here is N, which is load factor. So say the two, undo. Say the two, the W, CL max, rho, and S, say all of that equals 50. You can make your equation something like this. So if all that equals 50, it'd be 50 times the square root of the load factor would be our stall speed. And so if we're in straight and level flight where this is 1, then this would just equal 50. So I'm explaining, again, don't worry about this equation. The only equation you need to know if you're asked to calculate. So again, the question was, if we have a load factor of whatever, I think the question was 2, and a stall speed of 50, what would be the estimated stall speed in that load factor of 2? So if a straight and level stall speed is 50 and you have a load factor of 2, what would be your estimated stall speed? So this is what it's doing, is it's just taking, okay, your normal stall speed is 50, and you're multiplying it by the square root of the load factor. So in that example, it was 2. So in your calculator, you would just do the square root of 2, which is like 1.41 times 50, and you would get something like, I don't know, 70. Okay. So that's if you ever get asked to estimate the stall speed increase based off load factor, you take the square root of the load factor and you multiply it by the original stall speed. Hush. Sorry, my cat's meowing at me. So if you also look at this chart, okay, this chart said bank angle and increase in stall speed. So if first let's look at this one. So load factor and bank angle. So in this example, we said load factor of 2. So if we look at this and we say, okay, load factor of 2, at what bank angle do we get that? Well, we get that at all the way of a bank angle of 60. All right, so then if we look at this one and we say, okay, bank angle of 60, how much percentage increase in stall speed does that give us? Okay, it's about a 40% increase. So if we multiply 50 by, if we add 40% to that, that's the same thing as multiplying by 1.4. That's going to give us the same thing. So it's just this square root of the load factor multiplied by your stall speed is just these charts. It's just a shortcut for this chart. And the way they get this equation is from this equation. Hopefully I didn't completely confuse you guys. Just remember, if they say stall speed is, like I said, 50, what is the stall speed? What is the estimated stall speed at a load factor or N of 2 or whatever they say? You just take the original stall speed, you multiply it by the square root of the load factor. In this case would be 2. So 50 times square root of 2 to get your answer. So that's how you do those. And I apologize. I'm going to go actually review the lesson and make sure that that's in the lesson in the ground school. I've added to the notes to do it, just to make sure we kind of explain it, because it's possible you could get this on your check right. I don't think it's on the written exam, but it is still good to know.
Is there any more questions about the lesson tonight in general?
Just out of curiosity, when you're talking about like the graphs and things like that, I noticed in the tests that we do online through Part-Time Pilot, generally speaking, it's like, let's say the answer is 52. It's not 51, 52, and 53 as the options. It's like, in general, I'm guessing the FAA is not checking our math, but more or less that we have the concept. Is that kind of a correct assumption?
Yeah, so if I'm getting your question right, so yeah, I mean, they want you to like get the answer of the problem, but they want to know like that you know the concept too. Um, and that's what like, what the written, like that's what they're testing is like your knowledge of the subject areas. Is that what you're
Lonnie,
kind of?
what was the question? Sorry, I missed the start of it.
So I just have noticed that like when there's a test that's about like, let's say one of these graphs and the answer is 52, you're not like making sure we have our math down to a science. It like we're maybe able to use the graph and kind of get an estimate without doing the full interpolation. And so I was just noticing that like let's say the answer is 52. There's not like questions that are like 51, 52, 53, like you might see on a math test where it's giving you options that are nearby to make sure you're getting the exact answer. It's more the spirit of it, understanding. So you might have like 72, some of the low-hanging fruit stuff on there, like, if there was an
You're kind of
42
breaking up.
on there. So as long as I was in the ballpark, I was kind of okay.
Yeah,
Sorry,
no,
I know I'm driving.
that's okay. No, but I think I got your question. Yeah, so yeah, and you're right. The FAA is not going to have like options A, B, and C be like, in this example, like the answer was 70. They're not going to have option B be 71 and option C be 69, right? They're going to be more varied so that as long as you're on the right track, you should get the answer that's there. What they will do though is if there's like common mistakes people make that lead to a different answer, they'll put that in there, right? So if like, for example, a common mistake was people don't take the square root of 2 before multiplying it. They just do load factor times the stall speed, 2 times 50 equals 100. They would put 100 in there if that was like, a common error step in the process. So yeah, as long as you have the process down, on the FAA written exam, you should get and plus a lot of the stuff with like the graphs and stuff, there's human error. So like looking at the graph, like for example, and be like, okay, that was load factor 1.1. There's human error in picking on a graph too. So they understand that you might be off by 5 to 10% of the actual answer. So they're not going to put answers that close together. And as long as you're doing the process correctly, you should have an answer close enough to yours where you're like, okay, that one must be it.
Perfect. Thank you. That's exactly what I was asking.
Yeah. They're also doing less calculation. There's still, I don't want people to think, oh, there's not going to be any calculations. You still could get, that load factor chart. You still could get a weight and balance. You still could get, calculating ground speed or something. There still are there, but they're way less than they used to be. They kind of realized that like these specific calculations are, better tested in person than on a multiple choice test. So they're really focused on you getting the processes down, the and safety and things like that. Allie, you want to pull up the homework real quick, and then we could. I know people are probably itching to get out of here.
I hear you.
Over today.
Let's see. Oops, wrong one. Let me try this again. Okay. Let me go to tonight. Okay, so tonight, or due by next lesson is going to be ear and sinus, motion sickness, spatial disorientation, and illusions. So these are some of our aeromedical topics. Some of these, like, like motion sickness is pretty simple. Just make sure you're paying attention, especially to like ear and sinus and spatial disorientation and illusions. Sometimes those can get confusing. You guys have questions on those, just come to class on Friday and we'll talk about those. So our quizzes this week are on stalls, spins, weight, thrust, drag, wake turbulence, and ground effect, ear and sinus concerns, motion sickness, spatial disorientation, and illusions. And Friday this week, so I'm going to be covering for Nick on Friday, so it's just going to be me, and we're going to finish up. So we met Monday, and we decided that we were going to break these lessons up a little bit, just because there's a lot of topics when it comes to aerodynamics and this topic. So Friday we are going to also, besides like our Q&A and our giveaway, we're also going to start the lesson off with the left turning tendencies, adverse yaw, and some density altitude. And then after that, we're going to do our Q&A and a giveaway. So just know, like, if you saw that there, just know, like, we will still have time to cover like questions and answers. We just had to squeeze some of these in here just because like it would have been like super long. Like we would have been here probably until like 10 o'clock at night tonight. So that's why we decided to break up the lesson. So we will still be doing a Q&A. So come prepared with questions, and we will do a giveaway as well. So yeah, and I hope you guys have a good night, and we'll see you guys on Friday.
Yeah, good job, guys. Everybody that continues to show up, you're putting in the work, and proud of you. So keep it up.
Yeah, I'm really proud of all you guys. I'm glad that a lot of you are caught up, and we'll see you guys Friday.
Good night.
See you guys.
Good night, everybody.
Good night.
Bye.